Thank you, first of all, for the invitation, and thank you, Professor, I think it was Zhang, right, for kind of teeing me up here. And that's kind of leading me into what we want to do with Tribal here is build a platform for others to do excellent research, whether they're doing contact research directly or whether they want to add contact to their existing simulations that are using MFEM. I guess my name's Eric. I'm an engineer here at Lawrence Livermore. I work on Jamie Bramwell's solid mechanics and multi-physics MFEM-based code Serac, and I'm also working on the Tribal interface library. And so today I'll be presenting some new developments we've been working on in Tribal, and these are going to make it a lot easier to use Tribal with MFEM. So hopefully this group will be excited to take advantage of them. That didn't work. Okay. So first, a quick overview of the Tribal interface physics library. It's an open source code. Got the GitHub link right here. You guys will have the slides later on, so you can click that. So feel free to explore it. You can download it and use it. And the purpose of Tribal is solving the mechanical constraints that arise basically when solid materials interpenetrate. And for Tribal, we use Lagrange meshes as kind of the assumption there. Steve Wapshall has been the primary developer for the past 5 years or so. He's developed the contact methodologies you see there. I started on the team about 1.5 years ago. I've developed the domain repartitioning feature that we'll be talking about today and the MFEM interface. And Kenny Weiss has provided a lot of really valuable support for computational geometry and some of the computer science Axum related stuff. So Tribal's written in C++ 14. We've got a few dependencies. One's on Axum, and we use Axum for some of the CS tools, the data structures, for doing some computational geometry. And of course on MFEM, where the contact algorithms use MFEM data structures, and our ties to MFEM have gotten even stronger lately with the addition of the domain repartitioner and the new MFEM interface. So Tribal is open source this year, but it's been around at Livermore for over 5 years now. It's integrated with a few different codes here: AL3D, BLAST, Diablo, and Serac. So some of these codes are Fortran and mostly C-based, or some are mostly C-based. So Tribal's got interfaces to link with these codes. We can break Tribal up into 3 different parts, and I'll talk first about the contact methodologies. This is how we actually compute contact forces and Jacobians given some sort of mesh configuration. And there's a few assumptions we make in Tribal that make it difficult to interface with code like MFEM. First, we assume we have a surface mesh, which, typical problems contain volume meshes. We don't really have a surface mesh right away. Tribal also assumes we have linear meshes, and those meshes are usually bilinear quads. And finally, the third assumption is all of the methodologies in Tribal are really designed to work in serial, meaning that it doesn't have these contact methods don't have any knowledge of what's going on the other ranks. So to get around these 3 limitations of the contact methodologies themselves, we've developed some tools to help it make these contact methodologies more easily used with MFEM. The first is a domain redecomposer. And what this does is it takes, this gets around the limitation that the contact methodologies require things to be on rank, things to be basically serial. And the way it does that is it does it takes your domain, an MFEM par mesh metis partition domain, and it provides a repartitioning of it using recursive coordinate bisection. And that repartitioning gets all nearby elements on the same rank. And it also includes a layer of ghost elements, which you can see here. So these are just elements near the boundary. We call them ghost elements. And that ensures that any contact pairs that are near the boundary are caught, right? So you could have, for instance, an element that's on another rank um, and is interacting with an element on your current rank, and you would miss that pair if you didn't include like this layer of elements here. So that's the second piece of tribal. And the third piece, which ties the rest of it together, is the MFEM interface that we've recently introduced. And that gets around the other two limitations in tribal. First, that we require surface meshes. Well, MFEM has a tool for that called submesh, and that allows us to create that surface mesh on which we can compute our contact contributions. And finally, the other limitation I mentioned is that tribal expects linear meshes. Well, we've got in MFEM low order refined transfer maps, which allow us to take in a high order grid function and then map that over to a refined low order representation of the same mesh. So I'll be talking about all three of these now, since I think this might be the first introduction to tribal for a lot of the audience. I'll talk about kind of all of it, and then with the focus on the newer features that are more MFEM relevant. So yeah, first contact methodologies. Contact itself, the integral we're adding to our energy is pretty simple. It's deceptively simple, right? We've got we're integrating basically a pressure times a gap over some surface. But of course, the devil lies in the details. The pressure, that's just a Lagrange multiplier field. So, you can satisfy that using standard constraint enforcement techniques such as penalty or Lagrange multiplier or augmented Lagrange. For a lot of contact problems, augmented Lagrange is generally seen as the way to go. Right, but that's the first piece is pressure. Gap's a little bit complicated too. Notionally, this is the distance between two surfaces which might be in contact. So in order to compute this, first of all, you've got to pair two surfaces, which requires some computational geometry, some identification of nearby pairs of surfaces. And then the other complication is if you've got Lagrange finite elements and unaligned meshes, this gap is actually going to be C0 continuous over an element, which complicates integration if you're using, a typical tensor product quadrature rule. So to actually define the gap too, that's also isn't really clear. I mean, you've got this thing gap, but there's a million ways you can define it. Well, maybe not a million, but I mean, you can define it in terms of one surface. You can define it in terms of an average over the pair of surfaces. Also that kind of ties into the selection of the normal direction as well. Usually that's aligned with the gap vector. The other thing is you also have to define a surface of integration or an integration rule. So, first you got to build an integration domain. There's some choices involved with that. You can include maybe a plane which you project onto and do integration there, or you can integrate on one of the surface pairs. And you'll recall that the integrand is usually only C0 smooth. So if you really want to do it accurately, you've got to segment these surfaces over the element and really integrate over these segmentation pieces. Of course, you don't have to do that. There's plenty of approaches out there where you just integrate over the entire element with a higher order rule and just call it good. The point being, there's a lot of different choices you can make to enforce or to compute this contact energy. And it doesn't really end there, because when we want to take derivatives of this to get our gap and get our Jacobian contribution, these choices can really complicate those derivatives. You can get some pretty complicated terms in there. And a lot of these methods will even throw out some of these terms. You'll selectively choose ones which don't contribute very much, and you might take them out in order to simplify the computations that are required. So I guess the point is, there's a lot going on with contact, and and Tribal makes it easy because you don't have to deal with this, or you can use the methods that are enabled in Tribal and get away from having to define all these things yourself. So one of the methods in Tribal, this is used primarily in explicit finite element simulations, is the common plane method. It's very simple contact methodology, and in a nutshell, it works by projecting both of these surfaces to a common plane, and then we're going to enforce contact basically at a single quadrature point at the centroid of the overlap. So only the pieces that overlap, you're going to compute a contact force on that. And the force is just basically proportional to this gap. So it's a penalty enforcement technique. And you'll notice the number of constraints here is equal to the number of overlaps, which is not necessarily the number of nodes. So this formulation isn't stable in general. So that's why we use a penalty enforcement for it. The other main contact methodology that's in Tribal is the mortar method. So this is basically the method that's described in Puso and Larson's 2004 paper. The idea here is, unlike common plane, we've got a normal and a gap that are given with respect to one of the surfaces. So it's not quite symmetric. It's pretty close, but you do make a selection of one of the pairs in order to define your normal and your gap. The other thing that's interesting about it is we do actually do segmentation to perform integration here. This helps to improve the solver robustness, and it gives more accurate solutions. So let's see, did I want to say anything else here? So this is the method that we use typically in implicit solid mechanics. We use this in Serac, which is one of the codes I work on. And for this method, Tribal, it returns the forces and Jacobian contributions. So that by doing that, it allows the host code to choose its constraint enforcement technique. So in Serac, for instance, we've got penalty enforcement and Lagrange multiplier enforcement of the mortar constraints. Okay, so that's the first part. The second part is this domain decomposer. And so we talked about this briefly earlier, but Tribal's contact algorithms are designed for serial execution. And most problems of interest that we are looking at are parallel. They're scalable parallel problems. So, graph-based domain decompositions like the one that Metis does, it's not necessarily spatially proximate, especially if we've got some unconnected domains like we often do in contact. Here's an example of one here. We've got like an ironing problem, and we've got the indenter is on one rank. It's the red rank, and the substrate of it is this blue rank. So they're not going to see each other unless we do something to bring them next to each other. So, obviously the thing we do is we redecompose the domain, and we provide a contact version of so just the surface we're redecomposing. And now we bring basically this blue outline shows the surface elements on the rank, and then we also see that the indenter has the elements on the same rank. So, and then another benefit of doing this domain repartitioning as an explicit step is we're able to distribute the domains nearly equally among all the processors. So that way we can keep all the ranks busy while doing some potentially complicated contact calculations. So how do we actually use the domain decomposer? So step one, obviously, is creating this redecomposed mesh. And, you'll be able to go into the source. Once you've got the slides, you can click these links and take a look at the source online. But the idea is first you'll create a mesh, which does this redecomposition for you and creates maps going back and forth between these two representations. And once you've created the redecomposition, the next step is to create this redecomp transfer object. And this will let you move grid functions and quadrature functions back and forth between the MFEM par mesh and this redecomp mesh object. So the redecomp mesh object is an MFEM mesh. So anything you can do on an MFEM mesh, you can do on a redecomp mesh. And obviously one thing you can do is create grid functions and quadrature functions. So this sort of relies on that. You can create grid functions to store data on your redecomp mesh. And then finally, if you want to move Jacobian contributions from something on, say, a redecomp mesh up to a par mesh, you can create a matrix transfer object, and then these just requires arguments, your test and trial spaces for both the par mesh and the redecomp mesh, so basically the rows and column spaces of the matrix. And then again, once you've got these slides, you can click into these examples. We've got domain redecomposition example on the MFEM star mesh, or you can supply any mesh you want and see it work. We've got a matrix transferring the math matrix in this example here. And then we've also finally got this multi-domain thing, which is basically allows you to create one RCB partitioning of multiple par meshes. So if you have a use case for that, that's also an option. I didn't really talk about it too much, but yeah, that's and so finally the third thing is the thing that ties it all together is the MFEM interface. Of course, it's highlighted here, but in reality, it includes the contact methodologies in the domain decomposer, tying it to submesh and the LOR mapping. So yeah, that just kind of shows it here. So the way it works is basically the tribal contact methodologies, as I mentioned earlier, requires meshes that are on the surface, right? So that's what boundaries, that's what the submesh provides us as a surface mesh. It requires a low order mesh, which is what the LOR transfer gives us. And then it requires a serial mesh in the sense that it doesn't know about what's going on in the other ranks. So that's what this redecomp mesh provides us. So the simplified workflow that we would like in general would be something like so. We would give tribal, say, an MFEM par mesh. We tell it what boundary attributes the contact is on. And then we'd also give it a contact methodology and tell it, okay, go figure it out, do everything for me. And tell me what my contact contributions are, right? At the end of the day, give me what the forces are as a result of contact. Give me what the gaps are as a result of contact. Give me the assembled Jacobian, right? So the way we do that is through a few new methods few new API calls we've introduced into Tribal. The first is register MFEM coupling scheme. So this is meant to be called at the start of the simulation, and this takes the par mesh attributes and a contact method. And from that, it'll build your submesh, and if required, if the finite elements are high order, it'll build an LOR mesh as well. The next step is to call this update MFEM parallel decomposition. Typically, this is done within a time stepping loop, and when you call this, it'll transfer updated coordinates, velocities, and pressures onto both the submesh and the LOR mesh, and then it'll build a new redecomp mesh or basically an RCB decomposed mesh, and based on the new coordinates that it's received, and then it'll transfer all the data to this new mesh. So then the next thing you'll call is tribal update, and that'll actually apply the contact methodology, meaning it'll compute forces, gaps, and Jacobians on that redecomp or the RCB mesh. And then finally, at the end, we're going to want to know what those forces, gaps, and Jacobian contributions are. Well, we've got these getter methods, which not only return them, but they actually do all the transfers back from this redecomposed domain up to the lower refined domain, up to the boundary submesh, and then up to the volume par mesh. So that's kind of the workflow. There are a few examples available on the tribal repo. Here's one for the common plane, and then using the explicit finite elements, and then this is an implicit finite element example solving just a mortar patch test. So this has been this work is still a little bit ongoing. We're integrating these new features into a couple codes right now. The first is Serac, which is implicit multiphysics finite element code, which uses MFEM. Jamie Bramwell runs this code. I think she's in the Zoom call right now. And the other is Blast, which is an explicit hydro code, and it uses common plane for contact. So I'll focus a little bit more on what we're doing in Serac, just because that's that's on GitHub. You guys can download that and play with it yourselves. So the first problem I'm showing here is a twisting sphere problem. Basically, we've got a sphere pressing down and then twisting, and the interesting thing about that is, so as it twists, the contact force should remain the same. Even though the surfaces in contact are evolving and the domains, the RCB redecomposed domains are evolving. And so we can see we've done this on 3 ranks. As we press this ball down and twist it, we can see that as it twists, the force remains pretty much constant. So I ran this on a few different number of ranks, and the force was pretty much constant all the time. So you see a slight variation, but that has to do with the way the contact surfaces overlap. So you'll see a slight amount of variation, but in general, it's pretty smooth, which is what you'd like to see. And then also we've got a few more different examples, just the whole 3 different other examples we've got running. We've got an ironing problem, and then we've got a beam bending problem showing kind of the active set evolution down here. And then finally, we've got a twisting cubes problem. You can see all these run smoothly on multiple ranks, and then we can see the domain decompositions right here. So the outline domains are the redecomposed surface, RCB surface partitioning, and then the solid is the MFEM METIS partitioning of the volume. Right, so it's for ironing, you can see that as the indenter moves along, the MFEM mesh, the partitioning stays the same. Red is following the indenter along, but the surface mesh partitioning evolves. And it stopped playing on mine. Did it crash or something? Oh well. Anyways, same with the twisting cubes. Things are evolving as the cubes twist. I think PowerPoint crashed. Can you guys still hear me?
Yeah, we hear you. We can hear you.
Okay. Well, you guys will have to look at the conclusions on the slides later. But the main thing is I introduced these 3 main components of the Tribal Interface Physics Library. You guys can download it on GitHub. And coming next, in no particular order this fiscal year, I think we're planning on doing some work with GPUs and improving the contact algorithms and some of the physics capabilities, the interface physics capabilities, and just general code improvements. So I'll leave it with that. And yeah, thank you.
Thanks, Eric. Gotta say, I think you have some good candidates for next year's visualization contest.
Yeah, I'd like to see some of those next year.
Yeah, we got to scale it up. I think it'll be cool to get some of the fun little. Can we do movies for the Viz contest?
Yes.
Yeah.
All right.
Yeah, stick around. You'll see we have movies and still pictures.
All right. I'll keep that in mind.
Consider that as a commitment, so look forward to it. But we're a little over time already, but we can do one quick question at least. I noticed Joe had a question in the Zoom chat, so Joe wants to go ahead and ask his question.
Sure. I'm asking again because this is where my interest is at the moment. But with these cut boundary methods, could you could you conceivably use like an implicit surface that's embedded in a cut boundary to just have couple blocks that you're trying to do contact with, where the embedded in the block is in a regular shape, right? And then, you would use the implicit sign distance field to determine your contact distance instead of actually, modeling it as a geometry.
I haven't had too much of an opportunity to play with that stuff, but I did do some cut cell stuff in the past, and I always thought it'd be good to to merge the two. But yeah, I think you can do it with I think it's like a Nietzsche thing though, right? I think it's possible to do it, and I think like you said, the having the distance function in there kind of gets around having to compute the gap and might simplify things too. So yeah, it's a good idea.
Thanks. Because I think through matrix free and GPU being able to go completely matrix free there, you could accelerate solution time for every contact iteration.
Sure. Yeah.
Thanks. Appreciate it.